Hello, we're going to solve this problem of a cantilever in equilibrium. This is a very famous problem. It appears in many different forms. For instance, if I were to support my arm like this, that would be a cantilever. So what's a cantilever? A cantilever is a beam that extends beyond support. You can see many examples of this. You can apply to lots of biological situations, lots of medical situations that medical devices that actually use cantilever concept. Okay, so here is a very simple modeling of it. I have a beam, and this is for instance, in the swimming pool, the diving board is this is a diving board example. You have a diving board, but then over here you have a peg right through the board that prevents it from flipping over, right? And this one is just giving a horizontal, and you over here you can jump up and down and actually can create a huge amount of force that acts on here. But right now nobody's jumping up and down here, nobody's even walking on it. A very simple example. Just I want to know how much force is here and how much force is here, that's supporting just the weight of the beam. It's very straightforward. If there was something else, it would have to support that also. All right, let's see. First thing to do is identify forces that are acting on it. So we can leave this here and do another picture, or we can just draw it over here. Let's go with this. Already have, see, in the middle of this we have a center, and this is a uniform board, and that's where the center of gravity is, right? So we'll say, let me use a different ink to show the forces. So this is a big M times G. We can use letter W for it, right? What other? So over here it's resting, so there will be a normal force straight up from this. So let's call it N. We can call it N, and there will be normal force here also. But there will be also a frictional force. So you can see that when the board mass is this way, so it's going to want to go that way. If this was a pivot, it's going to go that way. Then it's going to push against this, the upper part. So we already know it's going to have to push down on it. So that should be a force. So we'll just call it F1. But then there's also a friction force that acts in the, this is like a normal force, but then the angle of this thing is not very clear. So we'll just say there is one more force that we don't know yet, and we'll just say it's act in that direction, because this peg will, you'll be pushing on it that way. So the peg will have to apply a force that way. So there's a force down and then the force right. So this F1 down and F2 right. So these are two other forces. So I need to figure out this and N. Well, let's call this guy F3. So we're using same notation. So with these three forces I need to figure out. Okay, so one thing we notice that if this was a XY plane, then all the forces are in XY plane, and so torque will be either in the Z axis or opposite Z axis. So while we are at it, we can just choose this direction to be X and this direction to be Y. So we just choose that. All right, so let's see. Let's work out torque a balance equation. I like to work out this first, and then there will be force balance equations, right? So torque balance equation, so number one, we need to pick a pivot about which we're gonna balance it. Well, I right now pivot is completely arbitrary, so we will pick a pivot at this point. If I pick a pivot, then torque of this and this will be 0, and so torque of this will have to balance the torque of that, and that will actually give me one equation. So let's see. So we have pivot at, say, A, and this point is B at A. Okay, so if you I'm going to just write the answers, but I want you to work out the torques. Torque of F1 is torque of F2 equal to 0. The torque of F3 is F3 times D, and you got to figure out why there is a lever arm. That's the lever arm, and this is counterclockwise. A torque of weight is weight times L over 2, and there's also the lever arm for this, and this is clockwise. So these and these lever arms you need to figure out. Okay, so if I take this a plus, then this will be negative. So tau net equal to 0. Adding all of this gives me 0. That's what the torque balance equation tells me. So I am going to say this is F3D minus mg L over 2, and that adds up to 0. So I solve this for F3. F3 is mg L over 2D. So I got one right away. Okay, now we want to balance force balance equations. We're going to get two equations because forces are in a plane. They go in both, they have both x and y components. So you look at sum of fx equal to 0. What will that give me? Well, I look at this guy. There's only one. This guy does not have x. This guy is f2. So I get f2. This does not have x, so that's 0. And so if I look at it, there's no other x, so that has to be 0. So f2 is actually 0. How about fy? Fy is equal to 0, so that will be f1 down, but y-axis positive, so minus f1, and f3 is up, so plus f3, and mg is down, so minus mg equal to 0. So f1, I can solve. F3 I already know, so I can solve for f1 is mg. Bring this over here. I'm sorry, f1 over that side. So I have f3 minus mg. So f3 is mg L over 2d. So mg L over 2d minus mg. So that's the f1. So we got f2, I got f1 and f3. That solves this problem. I hope you can see here very interestingly that if D was equal to L, suppose this support was not here but all the way here. So it's kind of an interesting check. That interesting check is I have one support here and another support all the way here. Then F1 should be, if this is mg, then it should be it should be mg over 2 this way and mg over 2 this way, right? So you can see when d equals to L, it will cancel out. Mg over 2 up, that's correct. But when I do d equals to L, the answer is minus mg, which is F1 was down, so it's actually flipped up. And so this is correct. So this checks the answer out completely. I hope this helps you build intuition about these problems. So take care. Bye.